Okay, so we're still on parallelograms. And so I've been given that ABCD is a parallelogram. And once again, a parallelogram is a quadrilateral or four-sided shape with opposite sides being parallel. And I've shown here that they are parallel. This time I have added two diagonals. Okay, so I went ahead and added those. We had added them earlier, but here I went ahead and put them in the picture. And I put the point where they cross, I'm labeling that as E. So I want to prove that line segment AE is congruent to line segment CE, and that line segment BE is congruent to line segment DE. So once again, my first statement is always my given statement. So I will say that ABCD is a parallelogram. And that's been given to me. Okay, well, next statement is that AB is parallel to DC. So I'll say that line segment AB is parallel to line segment DC. And that is the definition of a parallelogram. As we're using a lot of the same statements, a lot of the same reasons for all these proofs. So we need to be able to remember them and know when they come into play and why they're important. Okay. Now I can also say that angle ABE, so this angle up here, top right. So angle ABE is congruent to angle CDE, and hopefully we can all tell what this is. So angle ABE is congruent to angle CDE. And I'm also going to throw in that angle BAE, so this angle up top. So angle BAE is congruent to angle DCE, so this angle right down here. I'm going to lump those together. And hopefully we recognize that these are two parallel lines here, okay? And I have a line that's cutting through them. So a transversal there, the transversal here. If I'm looking at these two right here, they're on alternate sides of the transversal line. They're within my parallel line, so these are alternate interior angles. Same over here. I'm alternating sides of the transversal. They're inside of my two parallel lines. So these are both proven by the alternate interior angle theorem. Okay, awesome. And now, let's see, I want to prove that line segment AB is congruent to line segment DC. I wonder how we're going to do that. So I have line segment AB is congruent to line segment CD. Well, hopefully, if you've watched the previous two videos like you were supposed to, you will know that opposite sides of parallelograms are, let's go take a look. Opposite sides of parallelograms are congruent. We proved it earlier, and since we've proved it, we can use it as a statement. So I'm going to say that opposite sides of parallelograms are congruent. Sweet. So it's already helping us out here. All these statements that we're going to be talking about through, I think we're going to have 6 videos. Okay, these 6 videos can all be used as statements or reasons later on. Once we prove them, we can use them as reasons. So that's one of the main points of learning all these and doing these proofs. Okay, so now I've proven that these sides are congruent. So guess what? I have 2 separate triangles. So I have a triangle up top here. I have a triangle there. Okay, so I can say that these 2 triangles, I can say that triangle ABE is congruent to triangle CDE. Okay, so I have this triangle right there, and I have this triangle down there, and they are congruent because of angle, side, angle, angle, side, angle. Okay, and then now if we think about it, these line segments that I'm trying to prove, so I'm going to go ahead and write down that line segment AE is congruent to line segment CE, and line segment BE is congruent to line segment DE. So this is just our proof statement. Okay, so if I think about it, this line segment there, DE, is over here, BE, and they're both on this triangle. Over here I have AE and CE. That's on one triangle, that's on the other. This is on one triangle, that's on the other. And if you take this triangle, cut it out, and lay it on top of this triangle, they're going to be exactly the same. So I can say that line segment AE is congruent to line segment CE, and line segment BE is congruent to line segment DE through our CPCTC, or congruent parts of congruent triangles are congruent. These are congruent triangles. These are the exact same spots on the respective triangles, so they are congruent. So what did we learn out of this? Well, if we think about what's happening here, I'm saying that this line is equal to that line. And I'm saying that this line is the same as this line. And the only way that I can have two lines that are exactly the same length that are congruent is if I cut it in half. And what is common between all of these line segments? Well, E is, point E. So I'm saying that E is cutting line segment BD in half. I'm saying that E is cutting line segment AC in half. If we think about some terms that we've talked about, cutting something in half is the same thing as bisecting it. Okay, so this proof is basically telling me that the diagonals, line segment BD and line segment AC, are diagonals. So I'm going to say that diagonals of parallelograms bisect one another, or bisect each other, however you want to word it. And once again, we can use this the opposite way as well, and saying that if I have two line segments that are the same length, and that, or not necessarily the same length, but that bisect each other, okay, then they are a parallelogram. So if I have two line segments that bisect each other, then I can create a parallelogram out of them. Okay, so diagonals of parallelograms bisect one another, and we use that or prove that by this statement up here.